This reaction asks, predict the major product of the following multi-step reaction. So this is an example of a synthesis problem where you have multiple reactions designated by the 3 different arrows occurring to produce a product at the end of the reaction. So anytime you have a synthesis problem, you kind of have to take it one step at a time. So I would, for example, first look at what is produced after the first reaction, the hydroboration oxidation. Then I would look at what happens after the tosyl chloride and pyridine. And then finally, I would get to the last product. So always kind of draw out each step in a reaction like this so you don't lose your place. So let's go ahead and do that. So for the first reaction, we have hydroboration oxidation. So this is going to have anti-Markovnikov regiochemistry and syn addition. So that's the regiochemistry, anti-Markovnikov, and the stereochemistry, which is syn. So anti-Markovnikov means we're going to add to the less substituted side of the alkene. And in this reaction, we add a hydrogen and an OH group across the pi bond. So product number 1 is going to be this molecule right here, where we have kind of the original structure, 1, 2, 3, 4, and we've added to the 1 carbon. So that's adding the OH group. We've also added a hydrogen to the 2 position, but we don't typically draw the hydrogen atom in because it's bond line. So this molecule is a primary alcohol. And if we take a look at what is happening next, we have tosyl chloride and pyridine. Tosyl chloride, we talked about, is a way to convert a bad leaving group, the OH group, into a better leaving group, a tosyl group. So when we have this second reaction occur, we're essentially just converting the OH into an O tosyl group. And the tosyl group is going to be a much better leaving group for, say, a substitution or elimination reaction. The last reaction is going to produce our product. And in this case, we have sodium silate, which is a strong nucleophile only, in acetonitrile, which is an aprotic solvent, so polar aprotic. So our substrate is primary. We have a strong nucleophile only in an aprotic solvent, and so this supports an SN2 reaction occurring. And so the product for 3 is going to look like so. Whoops, let me draw that sulfur a little closer, like this. We were essentially bringing the silate in and doing an SN2 reaction to displace the leaving group. So if we take a look at what our possible products are, the one that corresponds to the answer we decided upon is answer choice number 2. So answer choice number 2 takes into the account that, we're always kind of just acting at that same alpha carbon. So the original kind of carbon that is bearing the OH group after step 1 right here is going to be maintained throughout the whole reaction process. So just kind of my thoughts on how to approach a question like this. Some of the key things to notice that might trip people up on this example are, number 1, that hydroboration oxidation reaction produces anti-Markovnikov regiochemistry. The second thing is a lot of people kind of forget about what tosyl chloride and pyridine do. So the pyridine, again, is just kind of part of that reaction where it removes the hydrogen atom that's left over on the OH group. Lastly, the key is to recognize that sodium silate is a nucleophile only and not a base. So if you had a base in that last step, you might produce molecule 5, which would be an elimination reaction. So really important to kind of keep track of, what type of reagent you have. Is it a nucleophile? Is it base? Is it strong? Is it weak? Is it small or is it big? So that's how I would solve kind of a multi-step synthesis problem.